Welcome to lecture 21. In this lecture, I continue the investigation of the near Minkowski limit of the equations that we have found as part of this course. Specifically found that when we were investigating the Bianchi identity back in lecture 19, we found that there are field equations that relate the tensors such as the Ricci tensor and the Ricci scalar with the energy momentum tensor T mu nu. And in the last lecture, we found that if we did a particular manipulation on another equation, namely the geodesic equation, we found that we could get Newton's law from these from the particular limit of the geodesic equation. So I think that the success that we got from considering the Newtonian limit of the geodesic equation means that we would be well suited to also consider the Newtonian limit of this set of field equations and see what it gives. So that's the plan for this lecture, is look at these field equations here and consider the near Minkowski non-relativistic limit of this set of equations. Recall that what we mean by this is that we are interested in the so-called peak field limit, where the metric tensor is given by the Minkowski metric tensor, which is just a diagonal 4x4 matrix with -1 in the time-like diagonal, plus a field h mu nu, which is taken to be smaller than the Minkowski tensor. So basically all the entries of h mu nu are supposed to be smaller than 1. And in addition, we restrict to situations where h mu nu only depends on the space coordinates, but not on time. So we have static situations in mind. Because it's static, it means nothing is moving. If nothing is moving, then consistently we also have to take the 4 velocities that appear in some of the equations to be equal to the 4 velocity of a particle at rest. So this means that the space-like part of the velocity is vanishing, and we just have a 1 in the time-like component. In addition, also recall that when we talk about non-relativistic systems, there's always this issue that we have the energy density that contains the rest mass energy. Rest mass energy is a huge amount of energy. And for non-relativistic systems, that is always much, much larger than the corresponding pressure of the system. So that means that whenever we have expressions that have both the energy density and the pressure, the energy density is always much, much bigger than the pressure. So the pressure can be neglected with respect to the energy density in the non-relativistic limit. Okay, so now these are our approximations. Let's use them on the field equations. Because we want to sort of rewrite this in a different form, recall that we can take the trace of the field equations, so contract this equation here just with g mu nu, and you find that the trace of these equations relate the Ricci scalar with 4 times this constant lambda minus this constant c2 times the trace of the energy momentum tensor. We can use this to plug it back into the field equations to replace r. So we just have an equation that links the Ricci tensor and constants and the energy momentum tensor on the right-hand side. Next, recall that we were fairly successful looking at the 0,0 component of the metric, linking that to the Newton gravitational potential. So guided by that idea, we also want to look at the 0,0 component of these field equations in the form 21.7. What will we need? Well, we'll need the metric tensor 0,0 component. Recall that by construction, we sort of write this as -1, that's the Minkowski part, plus the weak field perturbation, h00. And recall that in the last lecture, we found that we can relate the component h00 with the Newton gravitational potential, such that h00 is just minus twice the gravitational potential phi, and that's our metric component g00. For the Ricci tensor, we can again just use our computer program to calculate the 0,0 component of the Ricci tensor for this Minkowski weak field limit. Again, this is part of the mathematical file that you can find on the course website, and that will get you through the steps to get to this result. The main point is that the Ricci tensor 0,0 component is -1/2 times the Laplace of the 0,0 component of h. And using this replacement that h is just minus twice the gravitational potential of phi, we get that R00 is the Laplace of phi. In addition, we also need the 0,0 component of the energy momentum tensor, which, if you recall our lecture on fluid dynamics, ideal fluid dynamics, is given in terms of two terms. There's one term that is the sum of the energy density and the pressure times the 0 component of the fluid velocity squared, plus a second term where we have the pressure times the 0,0 component of the metric. Let's look at the energy momentum tensor in more detail. What we'll use is that this fluid flow velocity is normalized such that u mu is -1. That means, or that's the same as writing it as u nu with a metric g mu nu, or well, basically what that means is that we can, if we consider static situation, u vector is 0, we only have the 0 component left here. So if we read this equation from this side here, we get -1. And on the right-hand side, if only the 0 component of u is non-vanishing, we get u0 squared times the 0,0 component of the metric. Of course, we can also write this in terms of the combination where we have the upstairs metric and the downstairs fluid velocities. So this is the equivalent statement with the down, with u0 down. In the weak field limit, we can approximate the inverse of the metric tensor simply through the diagonal. So that means that the 0,0 upstairs component of the metric tensor is just the inverse of the 0,0 downstairs component. So what that means is that if we want to read this equation from this side here, so we have -1 is equal to u0 downstairs squared times the upstairs component of the metric tensor, and the upstairs component of the metric tensor is the inverse of the g00 component. We get that u0 squared first is -1 g00 upstairs. Because of this relation, this is then minus g00 downstairs, and g00 downstairs is just -1 plus twice the gravitational potential. So that's basically what we get for our u0 downstairs. We take the square root and recall that we are in the weak field limit where phi is much, much less than 1. The square root can be Taylor expanded to first order, and we find that the fluid velocity with index downstairs is just 1 plus the gravitational potential phi. So this is important. This means that there is a deviation from 1 for the fluid velocity component, and that comes from the metric tensor. Sorry, from the gravitational potential. Okay, so if we look at the energy momentum tensor, then what we find is that if we write all the terms that we have this combination of energy density and pressure times the u0 squared plus the pressure times the 0,0 component. If we now use the replacement of the 0,0 component of the metric tensor and the fluid velocity with downstairs component, we can plug this in and we find that the pressure between these two expressions just cancels because u0 has a plus phi and there must be a minus sign missing. Yeah, I'll fix the signs in the slides afterwards. So basically, the pressure between these two expression cancels, and what we find is that only the energy density remains, and we get the energy density times the fluid velocity squared. So we have 1 plus 2 phi here. In addition, we find that the trace of the energy momentum tensor, which is just minus epsilon plus 3p, is another quantity that we need for plugging together everything into our field equations. So Recall that I also said that in the non-relativistic limit, the pressure can be neglected with respect to the energy density. So that means that in this limit, the trace of the energy momentum tensor is just minus epsilon. So we have that we can replace the trace of the energy momentum tensor in terms of the energy density and the 0, 0 component of the energy momentum tensor also as the energy density plus the first order correction given by the gravitational potential. Putting everything together, our field equations then look like this. So we have, in particular, from the 0, 0 component of the Ricci tensor, the Laplace of the gravitational field. And from the right-hand side, we have the energy momentum tensor and this constant lambda that appear here. Since phi is much, much less than 1, we can actually neglect phi here on the right-hand side. So we only retain the 1 to leading order approximation. So the field equations become even simpler. And lastly, we want to assume that this constant lambda here is much, much less than the energy density. At the moment, this assumption is not grounded in any good reason because we don't really know what lambda really physically means. But eventually we'll see that this is a very, very good approximation. So we'll neglect lambda with respect to epsilon, and we find the following set of equations. It's just the Laplace of the gravitational potential phi is equal to a constant times the energy density. Okay, so that's the result. That's the weak field non-relativistic limit of our field equations 21.1. Laplace gravitational potential is a constant divided by 2 times the energy density. We want to compare this now to Newton's law of gravity, which says that the Laplace of the gravitational potential is given as 4 pi g, where g is Newton's g, or Newton's constant, times the energy density. You might have seen this law expressed in terms of masses. We can do this if we write the energy density simply as mass density, so meaning mass per volume, and then this looks more like your undergraduate physics, Newton's law, but the sort of form here is the one that we'll get if we replace mass density by energy density. The point to take away from this is that the field equations here and Newton's law of gravity look formally the same. The only thing that we need to do is we need to identify this constant here to give us this prefactor that we have in Newton's law, that we have 4 pi times Newton's constant. So the two equations, our field equations in the non-relativistic limit and the Newton's law of gravity matches if we assume that C2 is just given by 8 pi times Newton's constant. If we now make this choice that C2 is 8 pi g, the field equations that we started out making approximations of are then given by this equation here, 21.25. And we now know that these field equations give us back Newton's law of gravity in the limit where we have weak fields, small speeds, and small pressures compared to energy densities. So in the so-called Newtonian limit, these equations here contain Newton's law of gravity. However, these equations are more general than that. I mean, there is no reason to only use these equations in the Newtonian limit. We can also consider these equations away from the Newtonian limit, meaning for arbitrary metrics, arbitrary manifolds, arbitrary strong fields, arbitrary dynamics. And then these field equations here generalize Newton's law of gravity. Of course, these equations here are nothing else but the famous field equations that Albert Einstein wrote down for general relativity. And all we've done in the last few lectures is derive these equations from a set of first principle axioms, if you want so. So far, this is all we have. We have these field equations, and we know that in the weak field limit, they correspond to Newton's law of gravity. This by itself does not mean that these equations here are actually describing gravity away from Newton's law. So that means that we haven't really tested these equations yet. So we need to explore further what these equations mean, in particular in situations where we are not close to the Newtonian limit. Of course, you already know that people have done this over many, many decades. And as far as we know, these equations here really describe the laws of gravity extremely well. So we have not found any actual deviations in our universe of the so-called Einstein field equations. They seem to be maybe not the exact truth, but very, very close to what nature uses to describe the laws of gravity in arbitrary situations. And that concludes the present lecture.